Hi there. This is a realistic DevOps interview simulation focused on cascading failures, the kind of incidents where one small issue quietly triggers another and another, until suddenly the entire system is on fire. I want you to treat this like a real interview. Pause the video after each question. Say your answer out loud. Explain your reasoning as if I am sitting across the table from you. Then listen to a strong sample response and compare how you thought about the problem. If you want more interviews like this covering real production scenarios, subscribe so you do not miss the next one. Let us start with behavioral questions. Tell me about a time when a small change caused a much bigger issue than you expected. A strong answer here usually starts with acknowledging that cascading failures often begin with something that looks harmless. For example, I might say that I once approved a minor configuration change during a low-traffic window. On its own, the change was safe, but it increased latency just enough to cause timeouts in a downstream service. That downstream service started retrying aggressively, which increased load across the system and eventually triggered auto-scaling in multiple places. What I learned from that incident was not just technical. It taught me to think in terms of system behavior, not individual components, and to always consider retry behavior, timeouts, and load amplification when reviewing changes. Next question. When an incident is unfolding quickly and multiple things are breaking at once, how do you stay effective instead of getting overwhelmed? A strong candidate usually emphasizes structure and communication. I would explain that I focus on slowing the situation down cognitively, even if the system is unstable. That means clearly identifying who is leading the incident, separating investigation from mitigation, and resisting the urge to chase every alert. I prioritize restoring partial service or stopping the bleeding first, even if I do not fully understand the root cause yet. Staying calm comes from having practiced this approach before and trusting the process instead of reacting emotionally to the noise. Another behavioral question. Have you ever disagreed with the root cause analysis after an incident? How did you handle it? A good answer shows maturity and collaboration. I might say that yes, I have disagreed before, especially when the RCA focused on a single failure point instead of the system design. Instead of pushing back defensively, I brought data to the discussion. I walked through timelines, metrics, and dependency graphs to show how multiple safeguards failed together. The goal was not to be right, but to help the team learn something actionable so the same pattern would not repeat. One more. How do you balance moving fast with preventing complex failures in production? A strong answer avoids extremes. I would explain that I do not believe in eliminating risk entirely. Instead, I try to make risk visible and bounded. That means progressive rollouts, clear rollback paths, and designing systems that fail in contained ways. Moving fast is fine as long as you know how to stop quickly and safely when something goes wrong. Let us shift into technical scenarios. First question. In your own words, what is a cascading failure, and why are distributed systems especially vulnerable to them? A strong answer usually starts by framing cascading failures as amplification problems. One component degrades or fails, and that failure increases pressure on other components. In distributed systems, this happens easily because services depend on each other over the network. Latency, retries, and shared resources mean that a small slowdown can turn into a widespread outage. The key insight is that nothing fails in isolation. Systems fail as a whole because the interactions between parts are often more fragile than the parts themselves. Next question. Imagine a service starts responding slowly. What are some common ways that slowness can cascade into a full outage? A good answer walks through the chain step by step. I would explain that slow responses often cause clients to wait longer, which ties up threads or connection pools. Those clients may retry, increasing load instead of reducing it. Load balancers may mark instances unhealthy, shifting even more traffic to fewer instances. Auto-scaling might kick in too late or in the wrong place. Eventually, databases or shared caches become overloaded, and what started as slowness turns into hard failures across the stack. Here is another scenario. You notice that error rates are low, but latency is climbing across multiple services. Why is this dangerous? A strong candidate recognizes this as an early warning sign. Low error rates can be misleading because they hide queued work and back pressure. Rising latency means the system is struggling to keep up. If nothing changes, queues will fill, timeouts will trigger, and retries will amplify traffic. By the time errors appear, the system may already be unstable. This is why latency is often a better signal than error rate when trying to prevent cascading failures. Next question. How can retries make an outage worse instead of better? A solid answer explains that retries are a double-edged sword. When used carefully, they can hide brief glitches. But when a dependency is already overloaded, retries multiply the load at exactly the wrong time. If every request retries 2 or 3 times, traffic can explode exponentially. Without proper limits, backoff, and jitter, retries turn a partial failure into a system-wide collapse. One more technical question. What design patterns help reduce the risk of cascading failures? A thoughtful answer avoids buzzwords and focuses on intent. I would talk about circuit breakers to stop sending traffic to unhealthy dependencies, timeouts that are shorter than user patience, bulkheads that isolate resources between workloads, and back pressure mechanisms that force the system to shed load gracefully. The common theme is containment. These patterns do not prevent failure, but they prevent failure from spreading uncontrollably. We will continue building on these scenarios and push deeper into decision-making and trade-offs as the interview goes on. Let us go deeper. Imagine a real production system with multiple microservices behind a load balancer. One downstream dependency becomes intermittently slow, not fully down. How do you decide whether to cut traffic to it or keep trying to serve requests? A strong answer here usually starts with acknowledging that this is not a binary decision. I would explain that the first thing I look at is user impact. If partial functionality is better than none, I might tolerate some degradation. But if slow responses are causing thread exhaustion, queue buildup, or retries that affect unrelated services, then keeping traffic flowing is actively harmful. In that case, I would rather fail fast and degrade functionality intentionally. The decision is guided by signals like queue depth, saturation, and tail latency, not just error rates. There is always uncertainty, but the goal is to prevent instability from spreading. Next question. You are on call and see a spike in retries across multiple services at the same time. What do you do first? A strong candidate explains their thinking step by step. I would say that I resist the urge to restart everything. The first thing I do is identify what all those retries have in common. Are they targeting the same dependency, the same region, or the same database? Retries are rarely the root cause. They are a symptom. Once I identify the shared dependency, I focus on reducing pressure. That might mean temporarily disabling retries, increasing timeouts only if queues are under control, or even blocking traffic to the dependency entirely. The priority is to stop amplification before investigating deeper. Here is another scenario. Autoscaling is enabled, but during an incident, the system still collapses. Why does autoscaling sometimes make cascading failures worse? A strong answer recognizes the limits of autoscaling. I would explain that autoscaling reacts to signals like CPU or request rate, but it does not understand system health. If the bottleneck is a shared database or an external API, scaling up stateless services just increases pressure on the weakest link. That extra pressure can accelerate failure instead of relieving it. Autoscaling also takes time, and during that delay, queues can explode. This is why autoscaling must be paired with load shedding and dependency protection, not treated as a safety net by itself. Next question. How do timeouts contribute to cascading failures if they are set incorrectly? A good answer shows nuance. I would explain that timeouts that are too long cause callers to wait, consuming resources and blocking progress. Timeouts that are too short can cause excessive retries and false failures. The tricky part is that timeouts need to be shorter at each layer as you move outward in the call chain. If an upstream service waits longer than its downstream dependency, you end up with wasted work and retry storms. Getting this wrong is one of the most common causes of slow-moving outages that suddenly tip over into full failures. Let us talk about observability. During a cascading failure, dashboards light up everywhere. How do you decide what to trust? A strong answer focuses on correlation and sequencing. I would explain that I look for the earliest signal in time, not the loudest alert. Cascading failures create noise, so I try to identify which metric moved first. Often it is latency or saturation in a single component. Logs and traces help confirm the direction of failure, showing which calls started slowing before others followed. I do not try to understand everything at once. I narrow the scope until the story makes sense. One more scenario. You have identified a likely root cause, but fixing it will take time. Meanwhile, the system is unstable. What trade-offs do you consider for short-term mitigation? A strong candidate talks about containment over correctness. I would explain that short-term mitigation is about buying time. That might mean disabling non-essential features, reducing traffic from certain clients, or even intentionally failing requests quickly. These actions are not ideal, but they reduce load and protect core functionality. The trade-off is user experience versus total outage. In most real systems, controlled degradation is better than unpredictable collapse. These scenarios are uncomfortable by design. Cascading failures rarely give you clean answers. What matters is how you reason through uncertainty, how quickly you reduce amplification, and how deliberately you choose which parts of the system are allowed to fail. Let us switch gears and put you under pressure. You are the on-call engineer. Traffic is high, errors are climbing. Multiple teams are paging you at once. You do not yet know the root cause. What do you do in the first 10 minutes? A strong answer here sounds calm and deliberate. I would say that in the first 10 minutes, my goal is not diagnosis, it is stabilization. I acknowledge pages, establish myself as incident lead if no one else has, and slow things down. I look for the fastest lever to reduce load or stop amplification. That might be rate limiting, disabling retries, shedding non-critical traffic, or putting the system into a known degraded mode. I avoid deep debugging until the system is breathing again. Those first minutes are about preventing panic-driven actions that make things worse. Here is a harder one. You believe a specific service is the source of the cascade, but its owner strongly disagrees and does not want traffic cut. Users are already impacted. What do you do? A mature answer shows leadership without ego. I would explain that during an incident, consensus is ideal but not always possible. If the data suggests that cutting traffic will reduce harm, I would communicate that clearly and act. I would frame it as a temporary containment measure, not a blame assignment. I would also document the decision and the signals behind it. After the incident, we can revisit whether the call was right. In the moment, protecting the system and users matters more than being liked. Another scenario. You have two mitigation options. One is low risk but slow. The other is risky but could stop the cascade immediately. How do you choose? A strong candidate acknowledges uncertainty openly. I would say that I look at blast radius and reversibility. If the risky option can be rolled back quickly and affects a limited scope, it may be worth trying. If the risk could cause irreversible damage or data loss, I lean conservative. I also consider time to impact. If the system is minutes away from total failure, accepting some risk may be the lesser evil. This is never a purely technical choice. It is a judgment call under incomplete information. Next question. After the incident, leadership asks why this was not prevented. How do you respond? A thoughtful answer avoids defensiveness. I would explain that complex systems fail in unexpected ways, and prevention is about reducing probability, not eliminating it. I would focus on what signals we missed, what guardrails failed, and what we can improve. I would avoid pointing to individuals. Instead, I would talk about systemic improvements, like better load shedding, clearer ownership, or safer defaults. The goal is learning, not justification. One final question. How do you personally stay effective during cascading failures when everything feels out of control? A strong answer shows self-awareness. I would say that I slow myself down intentionally. I narrate my thinking out loud to the team. I write short notes as I go to avoid cognitive overload. I accept that I will not have perfect answers. Experience has taught me that calm, clear thinking is often the most valuable contribution during chaos. If you are watching this and felt uncomfortable, that is the point. Cascading failures are not about knowing the right tool or the perfect architecture. They are about decision-making under pressure with incomplete information, while the system is actively fighting you. Pause the video and think back through the questions. Which one was hardest for you to answer honestly? Which one felt closest to a real incident you have lived through? If you want more interviews like this, where the focus is on real-world judgment and not trivia, subscribe to the channel. The next interview goes even deeper into failure modes that only show up at scale. Thanks for watching.